Alright, let's talk now about mixed strategy games. And all the games that we played so far, these were games that were played in pure strategies. Pure strategies means that we actually think what the best strategy is in response to something else. But in mixed strategy games, even though it may sound a little bit weird, people don't really think anymore, they just do. To illustrate what that means is consider the game rock, paper, scissors. Under pure strategies, if your opponent plays rock, you know I should play paper. And if your opponent plays paper, you know you should play scissors. And if your opponent plays scissors, you know I should play rock. The problem with this game is that it will not have an equilibrium. I cannot always play rock because then the other one will always play paper and always will win. So the best thing that you can do in games that do not have a solution in pure strategies is to randomize your strategy such that you maximize your expected payoff. That is the whole purpose of mixed strategy games. And mixed strategy games often start with a game that does not have a solution in pure strategies. But of course you can also apply the idea of a mixed strategy to games that have an equilibrium in pure strategies. But it's more common to start with games that do not have an equilibrium under pure strategies. Okay, so let's take a look at what that means. So here we have a no Nash equilibrium game in pure strategies. So we already know games with two equilibria, which are coordination and anti-coordination games, as well as games with only one Nash equilibrium, which was the prisoner's dilemma. But what about the game that you see here? So we have two players, the criminal and the police. And the criminal could either hide in the woods or hide in the mountains, and the police could either search in the woods or search in the mountains. So if you play this game in pure strategies, what would be the criminal's best strategy if the police searches in the wood? Well, that obviously would be to hide in the mountains. So we underscore the 1 because 1 is better than -1. So what is the criminal's best strategy when the criminal thinks the police searches in the mountains? Well, then the criminal's best strategy is to hide in the woods because 1 is better than -1. So we underscore the 1 again. So now let's turn to the police. What's the police best strategy if the police thinks the criminal hides in the woods? Well, then the police's best strategy is to search in the woods, in which case it gets a payoff of 1 as opposed to -1 if the police searched in the mountains. And lastly, if the police suspects the criminal to hide in the mountains, shall the police search in the woods and get -1, or search in the mountains and get +1, and of course search in the mountains. So now you can see after we finish the game, we cannot identify a single Nash equilibrium. So this game does not have a Nash equilibrium in pure strategies. So again, what's the difference between pure versus mixed strategies? So the previous game between the police and the criminal had no pure strategy equilibrium. And a pure strategy is deterministic for every possible situation. Again, in the rock, paper, scissors example, it's deterministic that the player would play paper if the other one plays rock. But coming back to this example, the police will always search in the woods for the criminal. If the criminal is suspected in the woods, then the criminal will always hide in the mountains if the criminal expects the police to search in the woods. So how can a game with pure strategies and no Nash equilibria generate a Nash equilibrium? And the answer is that the Nash equilibrium is only possible if the players play mixed strategies or mix their strategies. In mixed strategy games, the players are assumed to just do something without thinking. So you can think of it this way: a criminal robs a bank, leaves the bank, and flips a coin to decide whether to hide in the woods or in the mountains. Likewise, the police receives an alarm, deploys some police to the scene, and flips a coin, and actually before it deploys anyone to the scene, flips a coin to decide whether to search the woods or the mountains. That would be a mixed strategy. So you don't really think anymore, you randomize your actions. So let's go back to our police example. So here we see again the game in pure strategies, and again it didn't have a Nash equilibrium because we had a situation like this where we underscored the positive ones for the criminal and we underscored the positive ones for the police. So now, what if both players play their strategies each with a probability of 50%? Then the question is, what is the expected payoff for the criminal? And I have showed you the math here in the lower panel. So for the criminal, the question is, what is the expected payoff if the criminal hides in the woods? So let's say the criminal robs a bank 100 times and always decides to either hide in the woods or in the mountains randomly. And likewise, the police randomizes whether it searches in the woods or searches in the mountains. So now what is the expected payoff for the criminal if the criminal hides in the woods and the police mixes its strategy randomly to search in the woods or search in the mountains? Well then, let's write it for the criminal. So the expected payoff for the criminal when hiding in the woods So when the criminal hides in the woods and the police searches there with a probability of 50%, then the criminal can expect to get a payoff of -1 with a probability of 50%. So we write -1 times 50%, although the 50% comes now from the police. So that's, and the criminal can expect to get a payoff of +1 when hiding in the woods, but the police ends up searching in the mountains. So in this case we have to still add plus a payoff of +1 by times the probability of 0.5. So the expected payoff is 0. Well, because the game is symmetric, we will have for all players a payoff of 0. But let's do it just for completion. Let's do the expected payoff, for example, for the police when the police searches in the woods. So expected payoff, police when searching in the woods. Well, in this case, the police searches in the woods. It can expect a payoff of 1 with a probability of 50%. So now we would say 1 times 0.5 plus -1 also with a probability of 0.5 and that also will give an expected payoff of 0. So we have to do that essentially 4 times, and actually we have to do that for each player. We have to calculate the expected payoff. So twice for the criminal and twice for the police. And this is what you can see in the lower panel of on the slide, where I have actually the expected payoff for the criminal and the police. And of course, for the criminal, the hide in the woods formula, which is -1 times 0.5 plus 1 times 0.5, well, that is the same under the search in the woods and search in the mountains. So they are the same. So that's why the game can be summarized like this. So we have again the 2 strategies, woods and mountains, woods and mountains. So the first one was the criminal, the second one was the police, and I'm not coding it now. And now the result of the mixed strategy can be simply written like this. Okay. So I hope this is clear how we model mixed strategies. So let's talk next about what the best strategy is that a player can play. So in a mixed strategy game, your best strategy is always to randomize your strategy such that you are essentially unpredictable to the other player. So if you think again about the rock, paper, scissors game, if you always played rock, that would not be a smart decision. And of course we have many other examples too, like in sports. Let's say if a goalkeeper is known to always dive to the left, of course the penalty takers will always shoot to the right. So the best strategy that you can do for games that do not have a Nash equilibrium pure strategies is to randomize your strategy such that you're completely unpredictable. So, and again, imagine you always played rock in rock, paper, scissors. That simply could not be a good strategy, because your opponent would then always play, let's say, paper when you always play rock. And likewise, a goalie who always dives to the right will be regularly beaten by penalty takers who shoot to the left. Okay, now let's take a look at another example. So So in this example, don't put too much emphasis on the logic behind those numbers. This game is just there to identify the optimum strategy for each player. So the question is, with which probability P should the criminal mix the strategies to hide in the woods or to hide in the mountains? So what is the best mix of strategies that the criminal can pursue? And again, the criminal strategy is to be unpredictable to the police, so that the police has no clue, no data points, or no historical evidence that would suggest the criminal is more likely to be there or somewhere else. Although what I just said is probably not exactly correct, because what the criminal wants to make sure is that the expected payoff that the police can get is the same when searching in the woods as it is when searching in the mountains. So what matters is that the criminal needs to make sure that the expected payoff for the police, so I don't know which color I shall make it, I'll keep it in black. So the strategy of the criminal is to make sure that the expected payoff that the police gets when searching in the woods is the same as the expected payoff that the police can get when searching in the mountains. And this is the criminal's objective. So how does the criminal make sure that the police is not more likely to get a higher payoff when searching in the woods or searching in the mountains? Okay, so now what the criminal needs to make sure, the criminal knows the payoffs, and the criminal can choose the probabilities to ultimately manipulate the expected payoff for the police. So the criminal knows that when the police searches in the woods, the police gets a payoff of 1 with a probability of P, which however comes, or which is decided by the criminal. And the police can get a payoff of 4 with a probability of 1 minus P. Okay, so now we always multiplied the probability with the payoff for the police when searching in the woods. So 1 times P plus 4 times 1 minus P is the expected payoff that the police receives when it searches in the woods. Like, imagine the police searches 100 times in the woods, then this is the expected payoff it can get. And that must be equal to the expected payoff when the police searches in the mountains. When the police searches in the mountains, they get 2, but with a probability of P. Which again the criminal chooses, and of course the criminal again wants to make sure that they are not predictable. Plus 1 with a probability of 1 minus P. So when that condition holds, the criminal makes sure that the criminal mixes their strategy such that the expected payoff for the police when searching in the woods is the same as searching in the mountains. Okay, so now if we solve this one, we can get the optimum strategy for the optimum mix strategy for the criminal. So we have to, okay, so now what do we get? Now I will just use one color. So now we have P, 1P, plus 4 minus 4P. That needs to be equal to 2P minus 1, plus 1 minus 1P. Okay, P plus 4 minus 4P has to be equal to 2 plus 1 minus 1P. Okay, so now maybe we can collect some terms. So we have here negative 3P plus 4 equals 1P plus 1. So now let's collect terms. So let's put 3P on one side, then we get to the right 4P, and we subtract also 1 on each side, and we get here 3. So then the solution is the P, the optimum P is 3/4. Okay, so the optimum strategy with which the criminal should play hide in the woods and hide in the mountains, that should be 3/4, and of course then 1 minus P is 1/4. Okay, so let's quickly erase this and let's do the same thing for the police. So the police wants to make sure that the expected payoff that the criminal gets when hiding in the woods is the same as the expected payoff when hiding in the mountains. Okay, so the criminal, so the police will make sure, so the police knows when the expected criminal hides in the woods, they can get an expected payoff of 4 with probability Q. 4Q. And they can get an expected payoff of 1 with probability 1 minus Q. So I just write 1 minus Q. So here to the left, this is now the expected payoff that the criminal can expect depending on the police's mixed strategies to search in the woods and to the mountains. And that needs to be equal to the expected payoff when hiding in the mountains. Okay, so the criminal can then expect a payoff of 1 with probability Q and a payoff of 2 with probability 1 minus Q. Okay, so this is the equation that the police needs to solve in order to have the optimal mix of strategies. Okay, so let's solve this one again. So now we have 4Q plus 1 minus Q, and that has to be equal to Q plus 2 minus 2Q. Okay, so then we get here 3Q plus 1 has to be equal to minus q plus 2. So now you can collect terms, and then we get 4q equals 1. So the police's optimum strategy to search in the woods is 1 over 4. And the optimum strategy to search in the mountains is then 3 over 4. Okay, so on the next slide, I have derived it again, and I also color-coded it again. So that should be clear now. So yeah, and good. And I just see this one here for the police. I should have made that blue, 1 minus q. That should have been blue. So that is the blue 1 minus q. Okay, but I think it is clear now. So if you follow those steps again, you should be able to replicate that, and we get the same result. The optimum probability for the criminal to hide in the woods is 3 over 4 or 0.75. The optimum q is 1 over 4. Okay, so now what are the implications of that game? And I have summarized it again here. So if the players play the optimum strategies, each player can expect to average out at the payoff of 0.75 over time. So let me just show that. For example, for the criminal, if the criminal hides in the woods, it can expect 4 with a probability of 0.25, so that's 1 plus 1 with a probability of 0.75, and that comes actually from here, search in the mountains. So 4 times 0.25, that's basically the expected probability when the police searches in the woods, and the 1 is the payoff for the criminal when the police searches in the mountains. But I had to write it down like this, and the reason why I had to write it down like this had to do with the accessibility requirements, because if I merge the cells inside, it will not pass the accessibility requirements. So apparently this is better for those who have vision impairments, although I'm not so sure whether that's the case. But anyhow, so we basically multiply through the payoff in each cell with the probability. So 4 times 0.25 plus 1 times 0.75. So again, we have to look again into those payoffs associated with each combination. And what I did here, I just replicated the formula. So you see 4 times 0.25 plus 0.1 times 0.75. I have written that twice, because again, I could not merge the cells, otherwise my accessibility checker would have complained about it. But anyhow, so when we take a look at the expected payoffs, and of course we can do that the same for the criminal when hiding in the mountains, then we would do 1 times 0.25 plus 2 times 0.75, that's all 1.75. And we can do the same for the police. If the police searches in the woods, they get 1 when the criminal hides in the woods, and 4 when the criminal hides in the mountains. So maybe you want to go back again to this original matrix. That makes it easier to understand the expected payoffs. But if we just summarize it in short, we could now summarize that game so woods, mountains, woods, mountains, and the expected payoff for the criminal and the police is always 1.75, 1.75, 1.75, 1.75. And that's for both, so I could replicate it if I had more space. So this is the expected payoff. So the expected payoff for all the players when they mix their strategies is always 1.75. So why is that an equilibrium? The best way to see that this is the best equilibrium can be seen if we assume that the criminal, whose best strategy is to play hide in the woods with probability 0.75, is now not playing their strategy optimally, or is not mixing their strategies optimally. So let's just assume that the criminal is a little bit not so smart and plays hide in the woods and hide in the mountains with a probability of 0.5. So now what would be the expected payoff? But the police still mixes their strategies optimally. So let me see if I can squeeze in again the original game, so maybe we can see it better. So the original game, I'll just squeeze it in here. Okay, so we had woods, mountains, woods, mountains. And again, the best strategies were, or the payoffs were 4, 1, and 1, 2 for the criminal, and for the was 1, 2 for 1. Okay, it's a little bit small, but so just to remember where those numbers come from. Okay, so we know nothing changes for the police because the police always plays the optimum strategy. So that means that the criminal can still expect to get a payoff of 1.75 when hiding in the woods, and also get a payoff of 1.75 when hiding in the mountains. So nothing has changed for the expected payoff for the criminal. So what we need to look at is at the expected payoff for the police. So the expect, and I just write it down slowly. So the expected payoff for the police when searching in the woods. So that is now to get a 1. But now the 1 does not come with a probability of 0.75, but only with a probability of 0.5. Plus the probability of 4, which now does not come with a probability of 0.25, but also with a probability of 0.5. So plus 4 times 2.5. So now the police can expect to get a payoff of 2.5 when searching in the woods. So now that has changed from 1.75 to 2.75. What's the expected payoff if the police searches in the mountains? So now the expected payoff, the police in the mountains. So now they would get 2 with probability 0.5. Plus the 1 also with probability 0.5. Oops, that should be blue. So that only gives an aggregate payoff of 1.5, which is less. So now the expected payoff for the police when searching for the criminal in the woods is higher than the expected payoff when searching in the mountains. So in this case, the police will only search for the criminal will always search in the woods every time. And of course, that will make the police better off than what the police would be off if the criminal played their optimum strategies, because then the payoff would be only 1.75. But the criminal not playing their strategy optimally makes the police now better off by 0.75. Okay, I hope this is clear how mixed strategies are being played. And yeah, let's just stop here and then continue with other concepts related a little bit to mixed strategies in the next video.